This is a graph of radioactive half-life, and this one is americium. You can see the half-life of an element is the time it takes for the element to reduce in mass by half its original mass. Now, the actual mass looks a bit different because americium can beta or decay or break down into a different substance. So half of this would be americium and half would be the new substance. But if it was 10 kilos to start, it would end up 5 kilos of americium and 5 kilos or approximately of something else, whatever it's decaying into. So the half-life itself is the time it takes for this to happen. That's one half-life. If you look at the graph, you can see the time for one half-life is the time it takes for the amount remaining to go from, say, 1 down to a half, or 10 down to 5, 20 down to 10. So the half-life here, if we go across and go down, is 16.02 hours. If you're going to put substances in the human body, you're going to want things that have a very short half-life. Technetium, 99 metastable, is the one that we often use. It's a gamma emitter and it's used to trace things around the body. It has a half-life of about 6 hours. So it's not in the human body in this form producing gamma rays for very long. Of course, the more you put in, the longer you have to wait before a fair bit of it's gone. The things that affect half-life include other things we worry about when we choose a radioisotope with a half-life. Is the half-life long enough to examine metabolic processes? So does it have time to be absorbed into tissues or transported around the body? But we need it short enough not to give the patient too much radiation. So you couldn't put anything in with a half-life more than hours. So you wouldn't put something in with a year half-life. It'd be in the patient for so long and emitting radiation, and it would hurt the patient or kill them. You need a rapid uptake into the desired tissue. So some radioisotopes we use, such as oxygen or fluorine, would be taken up by cell tissues. In particular tissues take up more. If we produce radioactive isotopes as part of a glucose molecule, then they might be absorbed more into tissues that have tumours because they absorb more glucose and they use more water. Also, we want rapid excretion. You don't want something that's going to be stored in fat tissue or in the kidneys or liver. So again, a chemical is chosen that gives compounds that break down in normal part of the body chemistry and are expelled from the body quickly. So half-life, very important and exceedingly important. In fact, you don't want these things to be in the body for very long, because the longer they're in the body, the more exposure the patient has to ionizing radiation.